Hello, this presentation is about my recent paper which is titled as Switchable Deep Beamformer for Ultrasound Imaging using AdaIN and presented in ISB 2021. I am Shujaat Khan and my co-authors are Jaeyoung and Professor Jong. We are associated with Bioimaging Signal Processing and Learning Lab at Department of Bio and Brain Engineering KAIST. The main idea behind this research is about how to design a deep neural network based beamformer that can be used for various applications. As in the current technology, a separate beamformer should be trained and its weight should be stored for different applications. And for different applications, we need different training data and memory and a lot of computational power to train those models. So to address this problem, here in this research, we propose a switchable deep beamformer that can be used to produce very type of a beamformer output such as DAS, MBBF, or various kind of a popular beamformer like DMAS or GCF, etc. And the same can be used to produce several post-filtration tasks such as despeckling and deconvolution by just using a single neural network which is trained at once only. In particular, we achieve this switchability with the help of AdaIN, which is adaptive instance normalization layer. And that adaptive instance normalization layer normalizes the channel data by a mean and a variance vectors, which are generated by a code generator network, which is simply a multi-layer perceptron neural network. Experimental results using in vivo and phantom data using focused ultrasound imaging confirm that the method can effectively generate various styles by just training at once, and the switchability with just simple switch code can be achieved. Let's start with simple beamformer, which is delay in sum beamformer. As we know, in ultrasound imaging, when the acoustic signal reflects back to the receiving probe, the receivers at different positions receive the signal with certain delays. That's why we call it delay in sum. The delay needs to be applied on different elements such that the signals can be focused at a point. And after focusing, we have coherent submission, Hilbert transformation, envelope detection, log compression, and dynamic range selection. In the proposed beamforming pipeline, all these green blocks were replaced by a simple neural network. This allows us to produce image domain output instead of just coherent submission output. This is important especially when we are trying to produce post-filtration tasks such as despeckling, because speckle patterns are more prominent in the log compressed domain. Another point which is important here is that conventional beamformer, for example MBBF or DAS, they generate one pixel by using single pixels channel data, like in this axis channel data. So to generate one pixel, they only need one vector of the channel data. However, for post-filtration tasks such as deconvolution, where we need access to multiple axial signals, and speckling, despeckling tasks where we need access to some neighborhood pixels, that's why we use this cubic data, which is composed of multiple depth planes and scan lines as well as the channel data. We call this cube a spatio-temporal data for universal signal processing. Finally, we need some post-training adaptivity so that we can generate various type of output from a single type of data by just simply changing the code. This is achieved by AdaIN code generator. The AdaIN is adaptive instance normalization is simply a kind of a normalization technique in which input, let's say in our case content, which is represented by X, like Mona Lisa image, and we have a style, which is a kind of a any painting that we want to copy the style from. And as you can see, the output, which is same Mona Lisa image, but has different style as Y. This can be achieved by this simple normalization rule, where first we whiten our input by subtracting its own mean and dividing it with its own variance, and rescaling to the style variance and by shifting it to the style mean. So to perform this style transformation or switching to the different styles, we need two vectors. One is mean vector and variance vector. However, we don't have any mean and variance vector in prior, which we can apply to our network to change the output. So to generate these mean and variance vector for different style, we design this code generator network and we assign one code to different style. For example, -1 is used for dash, and 0.5 is used for despackling, and minus zero point 0.5 is used for deconvolution, and so forth. And the last -4 can be used for the combination of despackling and deconvolution. So forth, you can have various other type of style, and the numbers have no particular meaning here. We can have 1, 2, 3, 4, 5, or whatever number we use. So these are just kind of our tags. And we need mean and variance values, which are unknown. So to train this network, we combine this network with our beamformer network. And when we train our beamformer network, for the same input data, when we change the desired output, we also change our style code. By doing so, the network will learn the gradient from output to the style code. In other words, when the input is fixed and output is changing and style code is changing, so the gradient will follow in this path so that the code generator network will learn what kind of mean and variance vectors are necessary for particular type of output. In this paper, I use my proposed switchable D beamformer to mimic 4 different styles or type of outputs as shown here. One is dash, second is deconvolution, third is despackling with the help of NNLR, where NNLR is non-local low-rank based despackling algorithm. And last is a combination of deconvolution and despackling. We train our model to minimize this loss, where O is a desired output, Z is a input cube, which is composed of spatiotemporal data. G is a network shown on the right side, and F is a code generator network, which is a part of this whole network, and C is a style code. The C is here. C could be any integer number which can be tagged to different style. For instance, -1 for dash, zero point 0.5, -0.5 zero point 0.5 for deconvolution, 0.5 for despackling, and one can be used for. So that number could be integer, real value, or whatever. So network will learn to map these values to generate these mean and variance factors. The architecture of the proposed method is composed of multiple convolution layer. In particular, we have 9 convolution block. Blue ones are the convolution block without any adaptive instance normalization, and the yellow is with adaptive instance normalization. For adaptive instance normalization, we get this WC, which is a combination of mean and variance factor for different channels, and it is generated with the help of code generator network, as I explained in the previous slide. Output is a RF cube data, and input is a RF cube data, and output is a beamformer output, and it is different for different style code. Here in this section, the reconstruction result of the proposed method are discussed. Let's start with the dataset. For the training and validation task, the RF data was acquired from 10 different subjects and different body parts were scanned, in particular trachea, carotid, thyroid, and artery regions were scanned with the help of linear array probe, which is operating at 8.5 MHz frequency. On the left side, you can see that the proposed method can generate 4 different styles by just simply changing the code. We compare our method with other adaptive beamformer and post-filtration networks such as DBF based deconvolution and MBBF and DES. In all these outputs, you can see that the method can successfully recover high contrast statistics. In particular, we use contrast ratio, contrast to noise ratio, and generalized contrast to noise ratio for the comparison of our model. Finally, the model was tested on independent dataset which was acquired from completely different anatomy which was not used for the training and different operating frequency. In particular, calf and forearm region of 2 different subjects were used and the scan was acquired using the same linear array probe, but this time the probe was operating at 11 MHz frequency. Here again we can see that the proposed method can successfully mimic all 4 styles by simply changing the code, which shows that the proposed technique is very generalizable. One important feature of our proposed method is that it can perform 2 competing tasks, which is deconvolution and despeckling, by just simply changing the code, because in despeckling, noise is suppressed by, by reducing the variance, while this deconvolution task usually require the enhancement of the high frequency component, which also increase the variance and noise component. But in proposed beamformer task, we can combine these 2 operations and we can achieve this by simply changing the code. Another important feature is its fast reconstruction time, which is several times smaller than the classical beamformer, deep learning based beamformer, in particular for deep decons, which takes around 10 times higher than this switchable beamformer. This study can be concluded as follows: that the proposed method can effectively perform computationally expensive post-filtration tasks and conventional beamformers all at once. And the post-training adaptivity is achieved with the help of AdaIN layer, which required mean and variance vector that can be generated by simple multilayer perceptron and can be trained simultaneously. Therefore, these methods allow easy implementation and can be an important platform for high-quality ultrasound imaging. In this study, we use some previous findings which are mentioned here. The first reference is about the adaptive instance normalization, and the second is for our target despeckling algorithm, which is non-local low rank based despeckling algorithm NNLR. We would also like to acknowledge National Research Foundation for the support of this study.